In this section, or in this chapter, we examine the electron arrangements, the arrangements electrons have inside atoms, and therefore, in this chapter, we examine the arrangements electrons take inside atoms and the resulting properties those electrons that In this chapter, we study the arrangements electrons take inside atoms and the properties that result from those arrangements. And so in the first areas, the first sections, we're going to look at the concept of electron spin and the magnetism that imparts on atoms. And then we'll look at the energies of orbitals inside atoms with multiple electrons. And then finally for this part, we'll look at the electron configurations of atoms. That is, which orbitals do electrons actually use inside atoms and ways that we represent that. So we're going to start by talking about electron spin. And electrons are too small to actually see, but we imagine or we think about electrons as having spin because we do know that electrons have magnetic fields. They impart a magnetic field around them. And charges that spin also impart a magnetic field, and because electrons are charged, we think of electrons as having spin, because they certainly do have magnetism. And we know that electrons can only have spin in two different directions. That is, if the electrons are held in place, that is, electrons can spin in one direction, in which case the north pole is up, or they can spin in the opposite direction, in which case the north pole is down. And we call those spin up and spin down. And they are represented by a quantum number, like we had other quantum numbers earlier, like n and l and m sub l. Spin has a quantum number m sub s, and it can be either plus a half or minus a half. And plus a half represents spin up, minus a half represents spin down. There's no difference in energy between those. There's no difference in the charge. The charge of the electron is still minus 1. It's simply a denotion of whether the electrons are spinning one way or the other way. Because electrons have these magnetic properties when they spin, molecules and atoms also can or might not have magnetic properties. And those properties depend on whether or not electrons, the spins of those electrons add up or don't add up. There are atoms for which electrons spinning in one direction or another direction. When we look at this, an arrow represents an electron. And we can have electrons next to each other that are paired, and those paired electrons will have their magnetic fields cancel each other, because one will be going in one direction, the one right next door will be going in the opposite direction. In an atom that has all paired electrons, that atom is diamagnetic, in which case it's not attracted to a magnet. It doesn't have an overall magnetic field. It's actually slightly repelled by a magnet. A paramagnetic substance is one in which each atom has one or more unpaired electrons making a magnetic field, but those magnetic fields for each different atom are arranged randomly. And so they're randomly in different directions from one another. A ferromagnetic substance, and that's what we think of as magnets in the real world. Magnets have unpaired electrons in each of those atoms, where each of those unpaired electrons are aligned with one another, so all of their magnetic fields add up, and you end up with a large magnetic field. And that's how a magnet, like a refrigerator magnet or a magnet inside an electromotor, works. Now what we're going to do is we're going to talk about how electrons are arranged inside atoms. And the most important thing is how they are, and what we care about is how those electrons are occupying orbitals. That is, what shapes they take. To do that, we have to know how many electrons can be inside a particular shape. And that's governed by the Pauli exclusion principle, which says that no two electrons can have the same 4 quantum numbers inside an atom. And the four orbitals, the 4 quantum numbers we looked at before, n and l and m sub l. N was just defined the shell, the principal quantum number. L defined the shape of the orbital, and m sub l defined which orbital in that subshell we had, and that mainly denoted the direction of the orbital. And so those 3 together define one orbital inside an atom. And because the m sub s quantum number, the 4th quantum number, can either be plus a half or minus a half, that means that there's only 2 different ways an electron can be inside an orbital, which means that an orbital can hold only 2 electrons. So that's the most important thing. And they have to have opposite spin. And so if we think about what's allowed, we could have a 1s orbital that has 2 electrons in it with opposite spin. That would be okay. We can have an orbital that has 1 electron with 1 spin. A box here represents an orbital. The arrow represents an electron, and the spin up or spin down is represented by the direction. So you could have an orbital with, say, a 1s orbital with no electrons in it. That's okay. You could have a 1s orbital with a single spin down electron. That's okay. What you can't have is you can't have an orbital with 2 spins in the same direction. That's wrong because they have the same ms quantum number. And the other thing you can't have is you can't have more than 2 electrons in an orbital. That's also not allowed. So you can have 1 or 2 electrons inside orbital or none, but if you have 2, they have to be opposite spin. Next, we're going to talk about orbital energies. And the idea that's important here is that when you have a single electron atom, and that means really hydrogen, or you can actually have ions, so you can have helium plus, which has a single electron, or lithium 2 plus, anything that has a single electron, the energies of the subshells depend only on the n value. The n value is the principal quantum number. So 2p orbitals and 2s orbitals have the same energy, 3s, 3p, and 3d orbitals all have the same energy, etc. When you go and you have multiple electrons, more than 1 electron, what happens is those electrons now interact and split these orbitals. So now the 2s and 2p orbitals are not the same energy as each other. The 3s and 3p and 3d orbitals are also not. The n equals 4 orbitals are not. The n equals 5 orbitals are not. And we get this essentially set of relative energies of the different orbitals, and that ends up being the order of filling that we'll see for electrons. So the question is, why does that happen? Why do these split up when you have more than 1 electron? When you have just a single electron, the only thing that really depends is on average how far the electron is from the nucleus. And for the n equals 2 orbitals, the n equals 3 orbitals, that ends up being the same for them. When you have multiple electrons, what happens is you have not only the attraction of an electron to the nucleus, say you have a proton there, and you have an electron here, you have the attraction of the electron to the nucleus, but what you have also is you have a second electron, and that electron is repelled from the other electron. So you now have electron-electron repulsions, as well as attractions of the electron to the nucleus. And the key is these electron-electron repulsions, which are called shielding, differ depending on the shapes of orbitals. So when you have different orbitals, an s orbital or a p orbital, that electron-electron repulsion is different for those two, and therefore you get different orbital energies for those. So whenever you have more than 1 electron, you get this set of orbital energies. When you have just a single electron, you get this set of relative energies for different subshells. That plays a role in which orbitals get used, as we'll see shortly. For most atoms, what happens is the orbital energies increase as n increases. So you'll see that as n goes from 1 to 2, it goes up, as 2 to 3 goes up, as 3 to 4 goes up, etc. That's the same as just a hydrogen atom. What's different than a hydrogen atom is that the energy increases as the subshell energy, as the subshells progress. That is, as L, quantum number L, increases. And so the p orbitals are higher in energy than the s orbitals. When you have s, p, and d, the d's are the highest. When you have s, p, d, and f, as in the 4th quantum level, the f orbitals are highest in energy. And so as you fill larger and larger, as you fill further and further higher L value subshells, those subshells are higher in energy for multi-electron atoms. So this all comes to play in what we call electron configurations, which is what we actually care about in this section. This is the purpose for thinking about this to this point. And that is that we have all of these orbitals, we have all of these shapes that we've talked about. These are a bunch of different shapes, and there are, of course, many, many more that electrons can adopt. They can be an S shape, they can be a D shape, they can be a P shape, they can be a 2P shape, they can be a 3P shape. Lots of different shapes they can have. If you have, say, 10 electrons in an atom, which of these shapes do they actually take? We now know that only 2 electrons can take any particular shape. Which of these would those 10 electrons take? And that's called the atom's electron configuration. And so what we care about is a listing of which of those orbitals we have, and the general rule is that electrons will fill the lowest energy orbitals first. So that's the general guiding principle we have, is that the lowest energy orbitals fill first because electrons want to be as close to the nucleus as they can, and they fill up from there. And so the rest of this section is going to be how we determine that. So the idea of electron configuration is that we fill the lowest energy orbitals first. So let's look at, say, sodium. Sodium has 11 electrons, and remember we can fill 2 electrons per orbital until we run out. So we can have 2 electrons in the 1s orbital, those are lowest in energy, 2 electrons in the 2s orbital, we've used 4 so far. We can fill 6 electrons into this set of 3 different 2p orbitals, so we now have used 10 electrons. We have 11 electrons, so that last electron goes in that 3s orbital. Remember, each box represents an orbital, so that box represents, this box here represents that shape there. And this box represents that shape there. There are 3 different ways we show that we use to note which orbitals electrons use. 3 different ways that we define electron configurations. One is the one we saw before, which is an orbital box notation. That's the most informative. It essentially lays out each orbital and how many electrons are in each orbital based on how many arrows we put in the box. The SPDF notation, also called the spectroscopic notation, essentially shows subshells and how many electrons are in those subshells. So on the bottom, we write the subshells, and on the top, we put the number of electrons in the subshell. So notice there's 6 electrons in the 2p subshell, and that's what that 6 is there. So the way you say this, you say 1s2, 2s2, 2p6, 3s1. Finally, we have the noble gas notation, which is the shortest and quickest. And the idea here is that that notation there, that chunk right there, equals the electron configuration for neon, which has 10 electrons. And so instead of writing all of this out and writing all of that out, we count that as just neon. So we put neon in a box or in square brackets and just write what comes after it. And so that's the noble gas notation. Now what we're going to do is we're going to look at the way that you can determine the electron configurations for all the elements, pretty much, of the periodic table, or certainly most of them. And we're going to do that by linking it to the position of an element on the periodic table. And we're going to look at a number of different things here. We're going to start with periodic blocks, and then we're going to go to what's called Hunds rule. So we're going to do that using a simulation where we have a periodic table and we click on different elements and it fills in the electron configuration in the box notation as well as it gives us the SPDF notation. So if we have hydrogen, the idea is that the electrons fill in from the lowest orbital up, so the electron will go in the 1s orbital, which is the least. If we go to helium, the second element, there are 2 electrons, so it makes sense that there are 2 electrons there. If we go to lithium, we would expect the next electron to go in the 2s orbital because it's the next one up. And indeed it does. And the same for beryllium. And then if we go to over here to boron through neon, we would expect to fill up the 2p orbitals because they're next up in energy. And in fact they are. So those fill up. And then of course sodium is next. Now in terms of periodic blocks, watch what happens to the highest energy electron, the highest energy orbital used, if we just go down from hydrogen. If we go to lithium, we're using the 2s orbital. If we go to sodium, it's filled up to the 3s orbital. Potassium, the 4s. Rubidium, the 5s. Cesium, the 6s. If we go to beryllium, we're filling up the 2s. Magnesium, the 3s. Calcium, the 4s. Strontium, the 5s. And barium, the 6s. So notice this area of the periodic table has the s orbitals being filled with those last electrons, and so this is called the s block in the periodic table. If we go over to this region over here, any element we click on in this region, the highest energy electrons used are in p orbitals. So in all of these areas here, if I go to arsenic, for example, it's the 4p orbitals. If we go to bromine, it's also filling up the 4p orbitals. If we go to phosphorus, it's the 2p orbitals. If we go to tellurium, it's the 5p orbitals, the highest up. So this is called the p block of the periodic table. In the center part here, where we have the transition metals, these are the d atoms, the d elements, and so they're filling up the d block of the periodic table. And finally, the lanthanides and actinides on the bottom are the F blocks. So in here, the electrons being filled up are either in the first row, the lanthanides, it's the 4f orbitals. In the lower row, the actinides, it's the 5f orbitals. So that's called the F block of the periodic table. The other thing is the number of electrons in that block is equal to how many atoms inside that block you are. So if you have boron, for example, you're the first element into the p block, and there's one p electron. If you go to carbon, you're the second element into the p block, and there's two p electrons. If you go to nitrogen, you're 3 electrons into the p block, and so there are 3 electrons. If you do, say, let's predict chlorine. Chlorine is in the 3p block, and it's 1, 2, 3, 4, 5 atoms in, so we'd expect 5 p electrons in its upper subshell, and in fact there are 5 p electrons there. If we went to vanadium, we would expect 3 electrons in this d block, and in fact that d block has 3 electrons. If we went to, say, nickel, let's see, for this d block we'd expect 1, 2, 3, 4, 5, 6, 7, 8 electrons into the d block, and in fact there are 6, 7, 8 electrons in that d block. So you can predict how many electrons are going to be in the highest filled subshell by doing that. Okay, so let's look at a couple of examples. Oh, before that, let's look at our chart. So the chart of how the periodic table corresponds to the electron configuration is the S block is this block over on the left, the P block is this block on the right, the D block is in the middle of the transition metals, and the F block are the lanthanides and actinides. Notice that the first two elements use the S block via 1s orbital, then we have the 2s, 3s, 4s, 5s, then the 2p, 3p, 4p, then we have 3d, 4d, 5d, 6d. Notice that the 3d orbitals fill after the 4s orbitals, and that follows that order of filling we had before. And the 4f orbitals are actually filling from about here, and the 5f orbitals are filling from right about there. So the next thing we can do is talk about using the periodic table to decide which orbitals are filled when. And we can do that simply using this general chart and just going through the periodic table. So the elements start here. So the 1s orbital is filled first, then the 2s orbital, then the 2p orbitals, the 2p subshell, then the 3s orbital, then the 3p, then the 4s, then the 3d, then the 4p. So you don't actually need to memorize anything having to do with this order of filling. You just use the periodic table, and all you have to know is that this is the S block starting at 1, this is the P block starting at 2, this is the D block starting at 3, and this is the F block starting at 4. Once you know that, you can just follow through the periodic table and know which orbitals are used in which order. So let's look at some examples. The first thing we're going to do is we're going to do Hunds rule, and let's do that using, let's say, oxygen. Hunds rule says that when you're filling up a subshell, you use the number, orbitals one at a time with the same spin before you start pairing them up. So let's go through this. Let's do boron first. So boron has its 1s orbitals filled. Remember, hydrogen and helium are the 1s subshell. Lithium and beryllium are the 2s subshell, so we'll fill those up as well. For boron, you would fill up this electron, this orbital here, with 1 electron. Now when you go to carbon, the next element, you have a choice. You can put the electron in the same orbital, or you can put it in a different orbital. If you put it in a different orbital, you can do it with the same spin or opposite spin. And Hunds rule says you put it in a different orbital with the same spin. So that's carbon. If we go to nitrogen, you do the same thing. You put it in a third orbital, and you do that with the same spin. Before you move on to oxygen, when you go to oxygen, then you start pairing up the orbitals. Oxygen is that. Fluorine has 5 electrons, and neon is where you've filled up the 2p subshell. Okay. Now let's look at using periodic blocks to determine where we are, and let's do chlorine. We know that hydrogen and helium is the 1s block, lithium and beryllium are the 2s block, boron to neon's the 2p block, sodium and magnesium are the 3s block, and chlorine is the 3p block. So because chlorine is the next to last element there, and it's 5 atoms in, What that means is we should fill up the 1s, the 2s, the 2p, the 3s, and the 3p up through the fifth electron, because we have 5 elements in. So instead of actually counting through, you can just fill in the 1s, the 2s. I always fill these in one at a time to remind myself of Hunds' rule. And then the 3s, so we're up to magnesium now. And now we're going to fill up our 5 electrons to chlorine. So do 1, 2, 3, 4, 5. And that's how you can do it, just based on the position in the periodic table. You don't even need to ask yourself how many electrons there are. You know how it fills up just from where you are on the table. Let's look at this in terms of the noble gas notation. So if we have magnesium, remember this is the 1s block, the 2s block, the 3s block, the 2p block, and the 3p block. So magnesium will fill up we'll fill up the 1s, the 2s, the 2p, because we filled up here, we filled up here, we filled up through here, and then we filled up the 3s, and we have, because magnesium's the second atom in, we do 2 electrons there. What the noble gas notation says is it says take everything below here, that equals neon. So that's neon, and then what we have left over are just those extra electrons in the highest shell, which is 3s2. So that's the noble gas notation. Now let's talk about this in terms of our idea we brought up earlier, diamagnetic versus paramagnetic elements. A diamagnetic element has all paired electrons. A paramagnetic element has at least one unpaired electron. It can have more. And so if you look at beryllium, beryllium has a pair and a pair. It's diamagnetic because it has no unpaired electrons. If we look at carbon, it has 2 unpaired electrons, so it's also diamagnetic. If we look at fluorine, it has 1 unpaired electron, so it's, I'm sorry, I said that wrong. Carbon is actually paramagnetic because it has 2 paired electrons, 2 unpaired electrons. Carbon has 2 unpaired. Let's look at carbon. Carbon has 2 unpaired electrons, so it's paramagnetic. Fluorine has 1 unpaired electron, so any unpaired electrons means it's paramagnetic. Neon has all paired electrons, and so it's diamagnetic. And so think about it. Where on the periodic table are you going to find diamagnetic elements, and where are you going to find paramagnetic elements? Okay, so let's look at a couple of harder examples. One using the D block. Let's look at iron. Iron's right there. So hydrogen and helium are doing the 1s subshell, well, not shell actually. Lithium and beryllium are doing the 2s. Boron to neon are doing the 2p. Sodium, magnesium are doing the 3s. Aluminum through argon are doing the 3p. Potassium, magnesium are doing the 4s, and then iron finds itself in the 3d subshell, and it's 1, 2, 3, 4, 5, 6 elements in. So what we're going to do is we're going to fill up to the 3d subshell, and we're going to put 6 electrons in it. So we're filling up the 1s, the 2s, the 2p, sorry, there are 2 electrons there, the 3s, the 3p, the 4s, and then for the 3D, we fill in 1, 2, 3, 4, 5, again following Hunds' rule, and then the 6th electron goes there. So iron would have 4 unpaired electrons, and it would of course be paramagnetic. Okay, there are 2 anomalies. One is chromium and one is copper. Chromium you would expect to have, similar to iron, except you'd expect it to have 4 electrons in the, I'm actually going to use the simulation for this. You expect chromium to have 4 electrons in its 3D subshell, but in fact, so you'd expect it to be this, but that's actually not what it is. What it is, if we click on chromium, it actually has 1 electron in the 4s and 5 electrons in the 3D. So that's just one of the things that sometimes the orbital energies are really close and it doesn't quite follow the rules, but most of them do. And for copper, you would expect it to have 9 electrons because it's the 9th atom in. So you would expect it to be that. What is a pair of electrons there? It's a little hard to see. You expect it to be that, but that's also not what happens. For copper, what happens is, similar to chromium, one of the electrons from the 4s that you expect there actually goes over and fills up the 3d. So the 3d has an extra electron, the 4s is short an electron. And so that happens sometimes, and those are the two main ones you should know.